right, let's get into chapter 10, which is about physics of fluids. And we'll start out with the definition, which is a little bit ambiguous. It's not really a very rigid definition, but it sort of gives us the idea of what we're clearly going to consider a fluid. We'll take a fluid to be a substance that can deform into any shape. When it's placed in a container, it will conform at least partially to the shape of the container. For example, like water does or like gas does. So those are our first examples of things that definitely are fluids, liquids, or gas. And everything we're going to consider in this chapter you can think of as either a liquid, like water, or like oil, or something like that, or a gas, like the gas that's surrounding us that we breathe, or, pure nitrogen or something like that. A book, clearly not a fluid. You put a book in a container, it doesn't, flow to meet up the sides of the container. There are ambiguous cases, things like jello, gelatin, certain kinds of mud might be fluids if it had enough water in it, or it might not be fluids if it didn't have enough water in it. So we're going to stay away from all those ambiguous kinds of things that maybe are somewhat like fluids, but not necessarily. We'll think of liquids or gases pretty much exclusively. Now a couple of properties of fluid, things that we can measure. The first one is the density of a fluid. And, we can define density of non-fluid things, but we'll mostly be concerned with fluids. So if we take a certain volume of a substance like water, we could measure the mass of that substance. And the density is simply the mass divided by the volume, or at least that's the average density. And the SI units, of course, are kilograms per cubic meter. One of the most important substances, of course, because it's so ubiquitous, is water. So the density of water is really easy to remember. If you take a cubic centimeter of water, about the size of those cubic sugar cubes, that amount of water would weigh 1 gram, or if you scale that up to SI units, so water's density is 1 gram per cubic centimeter. If you put it in SI units, that's 1,000 kilograms per cubic meter. Now, a cubic meter is pretty big volume, so it's not surprising that the mass is 1,000 kilograms that fits in a cubic meter. But, you can measure the densities of other substances. For example, you can look them up in a table in your book. Aluminum has a density of 2,700 kilograms per cubic meter. So if you need those, you can look them up in your book or on the web. On Quest, they may be given in the problem. If we take this equation, so density the symbol we use for it is the Greek lowercase rho, so we call this rho. Rho equals m over v, and we solve for m. We can calculate the mass of a certain volume of fluid as just the density of the fluid times the volume. I'm assuming this is a case where the density doesn't change over the volume that we're considering. That, when we use it in other formulae, it can kind of look confusing. So later on we'll see, for example, when we're trying to calculate the weight of a certain fluid, that's just mg. That's this. If I replace m by rho v, that's rho gv. So we'll see this rho gv's appearing in formulae, and sometimes they just appear a little bit confusing. So come back and look at this when you see that. Now, the density doesn't have to be the same all the way through a fluid. For example, our atmosphere is a kind of fluid, and it increases in density as you get closer to the Earth, or gets decreasing density as you get farther away. In a less physical example, you could imagine a sphere made of some kind of stuff that was very dense at one end and very not so dense at the other end. Something that's so there's more air mixed into it here, and then there's less and less air as you go to that end of the sphere. So the density of objects and fluids can change from point to point in the object. Here's a second variable, or something that we can measure about the fluid, the pressure. So pressure means if we have a little bit of surface and something's pushing on it, what's the force magnitude on that surface divided by the area of the surface? So force per unit area. And generally we consider pressure, even though force is a vector, here we're talking about only the magnitude of the force. So it's a scalar. we don't consider pressure to have a direction, and we'll elaborate on that a little bit later in these slides. Notice also that the symbol is P. It's the same as power and momentum, so that could be a little bit confusing if you weren't thinking about what you're talking about, but in any case, hopefully in problems it will be clear what the meaning of P is, that it's not a power rather than it's a pressure. SI units for pressure are force per unit area, newtons per square meter, and that ends up coming up so often that it's given the shorthand unit Pascal, PA. So pressure is measured in Pascal, at least in SI units. Here's an example. Let's imagine we've got a sort of cylinder full of water or some other liquid, and it's got a circular cross-section bottom. The table, or whatever it's resting on, is pushing upward on the cylindrical bottom. And so I want to find the pressure down here from the bottom surface. And the way I can do that is I want to figure out what the force from the table is upward on it, and I can use a free body diagram for the cylinder itself. The two forces on it, the weight force and the upward force from the table, have to balance out because this thing is not accelerating, and therefore the force from the table is equal to the weight of the whole thing. Calculating the pressure then, the pressure is just the force from the table divided by the area which the table is pushing on. So that's mg divided by pi r squared. So if we put in the numbers there, we get 624 pascals. That's the pressure. The pressure we think of as something that's a property everywhere on here. So that's the pressure here on the bottom, and here on the bottom, and here on the bottom. Pressure might change with position, and in most cases in fluids it really does change with position. Here's just a cooked up example that shows how that might happen. So here I'm imagining a wedge of iron sitting on a table, and you can imagine that if you put your finger underneath this thin edge over here, it might only push down on your finger a moderate amount, but if you put your finger under this really thick edge over here, it would be pushing down a lot. And so since the force seems to be changing, that means the force per unit area might be changing as you go across. So we're going to calculate, or at least imagine calculating, the pressure from the upward force from the table divided by the area. Now we don't want to use the entire rectangular area of the bottom of this because the whole point is the pressure is changing. So what we need to do is divide up the bottom into little tiny bits of area. And since most of the important stuff is going on as we move from left to right, not from front to back, we're going to divide up conceptually this wedge into a bunch of strips. I've drawn them as kind of thick strips here, but we could imagine really thin ones if we wanted to get a fine-grained sense of how the pressure on the bottom changed. So I'm going to calculate the force on this little thin strip here, or imagine calculating it and doing the same for all the strips of the bottoms of these chunks of metal there. And if we do that, we would find that the force, upward force from the table, is largest on the right-hand side, and then it decreases as we go down and to the left. And therefore, if we did a very fine division of the iron wedge and calculated the pressure as just the magnitude of the table force divided by the area, we would find that the pressure at the left end was very small, and then it got bigger and bigger and bigger as we went to the right. So that's just an example of a case where the pressure might change with position. And in general, we should assume the pressure is changing with position. Here's one case that we'll find out about exactly how to calculate this later on. We'll find that, for example, here's a, like a graduated cylinder or something like that. I've got it filled up with some fluid, and there's some pressure from the fluid on the wall. And in general, we want to think of pressure as being due to that microscopic molecular motion of the molecules drumming against the inner glass surface there. They're pushing on it as they bounce off of that wall, and that's the source of the pressure in there. So we'll find out later on that the pressure actually increases as you go down in the fluid, so that if we made some measurements, we might find out that up here at the surface of the fluid, it's 101.3 thousand pascals, and then it starts increasing slightly as we go further down in the graduated cylinder. In fact, the pressure on the inside of the glass cylinder is still 101.3 kilopascals up here, even when there's just air on the inside. And that's because, we don't really notice the air pressure around us, but we're in the middle of a fluid that has some pressure, and the air molecules are always drumming on whatever they're in contact with. So on the inside of the cylinder, they're bouncing off of it and sort of pushing on it, exerting a force on the inside of the cylinder, also on the outside of the cylinder too, but here we're just concerned with the inside. So once we get out of the liquid, the pressure actually stays roughly constant here. Now, of course, it would actually go down if you went way up in the atmosphere, but it's not changing too much over small laboratory heights there. Okay, and again, this is just a picture to remind me to say it's always useful, or sometimes, you can confuse yourself about pressure, but one way to make yourself less confused is to imagine that pressure is really due to that motion of molecules bouncing off of surfaces and off of each other in the fluid. Let's talk now about some properties of pressure in fluid, because they're really not intuitive. Most of us don't have too good of intuition about fluids and pressure, so these need to be stated explicitly. The first one is that even though we've been talking about pressure as if there's some solid surface that the fluid is pushing against in order to define the pressure of the fluid, we don't need any surface. In other words, in the middle of the ocean, when you're down in the middle of the fluid, there's a pressure, perfectly well-defined pressure there. And we can think of it as just, I could, in my mind, imagine a cube of fluid sitting here and an adjacent cube of fluid right next to each other. They're sitting next to each other and they're each bouncing off of each other, and those molecules bouncing off of each other are what generate the pressure down there. So there's pressure even in the middle of the fluid. We don't need a solid surface like the outside of the cylinder for it to be defined. Second property is that if the fluid's in static equilibrium, then the pressure is defined as the force on a surface area divided by the area, and you might think that it would depend on which area you use. In other words, how I orient that surface area. It doesn't depend on the size of the surface area you use, because if you make the area half as big, you'll have half as big of a force, so that's not so surprising. But it also doesn't depend on the orientation of the surface that you use, and that's why we only talk about the pressure being a scalar quantity. It doesn't necessarily have a direction, because even though it is pushing in lots of different directions, there's no sense that we need to keep track of that, because it's the same no matter how you orient your surface. Let's think about how to justify that. You could, in the middle of a container of fluid, in your mind divide out a little cube of fluid. And again, this property that the pressure is independent of area is only true if the fluid's at rest, if it's in static equilibrium. I'm not sure if I just mentioned that a second ago, but the fluid's got to be at rest for this to be true. And then this pressure is the same in any direction. Why is that? Well, let's imagine on the 6 sides of this cube, suppose the right side pressure were bigger than the left side pressure. If that were true, then the cube would start moving to the right. Bigger pressure on the right, smaller on the left. That would mean an imbalance in the forces, and that would violate our assumption that the fluid's at rest, that it's in static equilibrium. Similarly, the top and the bottom have to balance, the front and the back have to balance. Now, suppose those do balance, it's also got to be true that the top and bottom pressure have to be equal to the left and right pressure. Why is that? Well, that's because, let's suppose the left and right balanced each other out, but they were smaller than the top and bottom kind of pressure, so it depended on the orientation that you were looking at. In that case, if the top and bottom pressure were larger, that little cube shape would start to flatten out and widen horizontally. So again, it wouldn't be in static equilibrium if that were happening. The fluid would start moving. So if the fluid's just sitting at rest, and when we say at rest, we mean macroscopically speaking, there are no currents in the fluid. We don't mean that, of course, always at the molecular scale there's lots of motion, but we mean no macroscopic currents. Okay, so that said, there's only one pressure as a function of position in the fluid. It can change with position, but at any location in the fluid, it doesn't depend on the orientation. Next property. Also, if the fluid's in static equilibrium, then the direction of the force associated with pressure is always perpendicular to the little bit of surface that you've chosen. Okay, that's true in the middle of the fluid, and it's also true at the container surface. Here's an argument for that. If, let's suppose, for example, that we've got a fluid in static equilibrium, and let's suppose that it's pushing on the edge, the container, in a direction that's not exactly perpendicular to the surface, but it has a component which is parallel to the surface. So it's pushing in this direction, so there's both a perpendicular and parallel force component. If that were true, that means the fluid is pushing on the wall of the container, at least partially in the direction parallel to the surface, and that means by Newton's third law, the wall has to be pushing down on the fluid at that position, and that means that the fluid would start to move down along the wall, and that would violate the fact that the fluid is supposed to be in static equilibrium. So the real picture is that everywhere on the surface, whatever orientation that little bit of surface that the fluid is bunched up against, it's exerting a force in the direction completely perpendicular in the outward direction. Finally, we'll take a break right here, but our last one, we're going to use this to calculate with, so before we derive it, we'll take a break. But it tells us that as you move down in the fluid, further and further closer to the Earth, the pressure increases, and it tells you exactly how it increases. So let's take a break there, and we'll come back and talk about how to derive this and use it in problem solving.